So we have looked at a couple of problems that can be done both with a force approach and also the energy approach, right? A couple of kinematics problem. Now let's look at a problem where we could not do with the force approach, and the energy approach is sort of actually it's doable, but it's going to be really complicated. And with the skills we've learned so far with the kinematics equations and the Sylvat equations, we couldn't really do it. But with the energy approach, it's a piece of cake. All right, it's this roller coaster problem. So we'll split into bits, right? So there's a lift hill, you go up. Let's go with our favorite numbers, 30 meters, 10-story high roller coaster. Not the highest, but it's pretty good. And now it's going to go through a loop and a couple of bumps. We're going to worry about it later. Let's have the problem to ask, what is the force you will feel at the top of the loop? So it will go down, right? And over here, what is the force over there? Well, what are the forces that you will feel anyway? So first of all, there is the weight of the coaster. So I'll ask what does the coaster train actually feel? Okay, so it'll feel or what is the forces on it? So there's the W, and there is also the normal force. Okay, and these will work together to be the centripetal force. Okay, so the centripetal force on the coaster car will be this plus this. Okay, so we can know that this is the mass of the coaster, right, times G, like that. So we know W is that. Okay, so what will you actually feel? Remember, we had a whole video talking about you don't actually feel the weight. What you feel is the normal force. So what you're pushed against over here. So let's say this is our ultimate goal. Okay, so this is our goal. So let's say we know the mass. All right, the mass, let's say, is of the car itself, let's say just 20 kilograms. Okay. Pretty light car, but that's gonna do. It's wooden coaster or whatever. So this is our aim. Okay. So how do we find n? Well, we need to know the mv squared over r, right? So we need to know the radius. We need to know the speed, like that. And let's say the height of this thing is going to be 20 meters. Okay. So all right. So we have some numbers over here. So let's see, what do we know? We know. Let's check off things we know. If I get a different color, here, let me use green. So I'm given that. I know G. So what's the M? The M is the coaster, right? So I also know that. Do I know R? Well, if I know the height of this, assume it's a circle. Then the radius is 10, right? So we do know R. It's going to be 10 meters. Everything's in SI units. So now I will need the velocity, or the speed, I should say, right? No vector sign, right? Remember the difference between this and this. This is the magnitude of this, right? So the speed, we need to know that. Okay. How do we know the speed there? Well, let's say at a lift hill over here, it's technically there will be a little bit of speed, but let's say it's sort of just over the top, and this is released at rest. Okay, so the V equals to 0 over here. Okay, so now imagine you only know kinematics equations, so the Sylvats, right? How will you do this? Well, you can kind of just about find the velocity over here. Assume this is a straight line, then this is a straight decline, straight incline or a straight decline. Then you can do sort of like inclined plane. You can resolve. How would you do that, right? So remember, if it's over here, you will need to find the weight, and then you will have a normal force, and then you want to find the acceleration this way. So because to find Sylvat, you need the acceleration. So you need Wx, Wy. Find the angles. You need to. I don't think you even could, because I haven't given you the angle over here. So you're not going to be able to find the speed here or the speed here. But let's say even if you go out and measure the angle, it's quite an annoying thing to find the A, right? So I don't know if you remember from the example, it's going to be G sine theta. I've just done inclined planes enough times in my life that I remember that's going to be the acceleration. We can check that, right? If the incline here is 90 degrees, so sine of 90 degrees is 1. So you'll have A equals to G, so that kind of makes sense. If this is perfectly straight, perfectly vertical, I should say, then it's just gonna be free fall. Anyway, that should be the right answer of an inclined plane, but that's assuming this is a straight line and I know the angle. And then you can use SUVAT, but that will only tell you the final velocity here. And then up here, the problem is here, A is a constant, right? Well, no, that's not a problem. The problem is A is not a constant there. If you look over here, the incline, if we treat this as a straight line, okay, this is a constant, G is a constant, so A is a constant. SUVAT is fine. Kinematics is fine. Over here, the acceleration is constantly changing, right? The acceleration is different everywhere. So in this first period, let's say from point 1 to point 2, sure, I can kind of still use SUVAT to sort of finagle it and find the V2 over here. But if I want to find V3, this is going to be our point 3. So if I want to find the velocity or the speed over here, I should say, right? There's no hope because from 2 to 3, the acceleration is different. It's pointing towards the center, right? So at every point, the acceleration, its direction is changing and the magnitude is changing as well. Okay, so that is this is a vertical circle. So yeah, the magnitude will be changing. It's so it's almost impossible to find it there. Okay, now let's try to find use the energy approach. Okay, so again, you can use E1 total equals to E2, but I am going to so you can use that method, or you can use change in K. Is so the gain in kinetic energy is the loss in potential energy. Okay, so what is, I don't have space to write out the K, and so what you might want to do just when you're getting used to it is K1 equals to what, U1 equals to what, and at this point I can directly compare point 1 and point 3. Okay, you could go through for point 2, but I can directly find K3 and U3, and then you can match, so not 1 and 2, you can match 1 and 3 in this case, right? So K1 plus U1 should equals to the kinetic energy at point 3 plus the potential energy at point 3. You notice I say potential energy, I mean gravitational potential energy, but we're only going to talk about one type of potential energy. So sometimes people are lazy, including me, and not just say potential energy. No one appreciates the gravitational energy, but yeah. Okay, so yeah, well, I'm gonna look at the change in kinetic energy being, right, so that's gonna be final minus initial. I'm gonna do it with this method. So 1/2 mv3 square minus 1/2 mv1 square. Okay, so m doesn't change. The mass, hopefully no one fall out of the car during this process of the roller coaster. So the mass of the coaster is gonna be the same. And the speed V3 and V1 is different, right? So we want to find this, and we're starting at rest. Okay, so that's going to be 0. And now, what's the change? So minus, what's the change in potential energy? Well, let's just put that in. So we have mgh. So mgh needs to be here compared to here, right? So I'm going to set the sensible choice, h equals 0 for the ground level. So I can put that in the diagram. That's good enough definition. So anyone grading the problem will be able to refer to the diagram. And the height there is final. Oh, sorry, final. Good. So final is 20, right? The height over here. And minus mg initial 30. Okay. So we have essentially 20 minus 30. So that's negative 10, but you have a negative, you can figure this out. So it's going to be mg times 10, okay? Essentially, you can also think of that as minus delta u. This is another way of doing it. You can do u3 minus u3 minus, so u meaning potential energy, u3 minus u1, or you can do this, right? Delta h, and delta h just means final minus initial. And what's the change in height? It has decreased by 10 units, right? You can just do the displacement kind of concept instead of the absolute. This is the absolute value at 0.3, absolute value at 0.1. You can do the absolute value, subtract it, or you can just do the change. And the change is negative 10, right? From 30 to 20. So you can put in negative 10 over here. Either way, you'll get mg 10. Because negative, negative. right? And we have this here. The mass cancels as far as the velocity, the speed is concerned, and now you can find v3 square is 2 times g times 10. Okay, and v3 is positive negative square root of let's plug in that as 10 just for estimation. You can do it properly in your homework and in your exams. So this is 100, 200. So, and we're going to pick the positive square root. You're going to put in the correct significant figure, whatever the problem is given, and the unit. Significant figure, not so important. Unit, most important. And we can say reject negative, since speed is positive. Okay. This is for completeness. This is the most important thing. It's up to you whether you write this or not. In an exam, again, if you don't write it, no points will be deducted, but it's always good to have in terms of presenting the solution. So within just, if you think about it, I've sort of some redundancy over here, but technically, 1, 2, 3, 4, 5, 4 to 5 steps, you got the velocity. Notice I have no resolving any angles. I did not really resolve any XY angles, nothing, really just comparing the MGH, what's the change in height, or just do final minus initial, taking into the minus sign, and find the speed, and you're done. So I know the speed here, the mass does not fall into the equation over here, but it's useful to, in here, to find the force, right? So I now know the centripetal force for it to be able to successfully go in a circle, and I will know what the n is, right? So the n, which is the apparent weight, as we talked about, because apparent weight is the weight you feel, you never feel your actual weight. Okay, so it's counterintuitive, right? Just a quick reminder of that video. If you're standing here, what's your free body diagram? Your free body diagram is W and normal force. Because you're not accelerating up or down, your n is W. So you think you feel your weight, but it's the same. So what you feel is actually the ground pushing you up. If you think about it, right? Just you're sitting here in your chair, I'm standing here. What I feel is really the force. I don't feel anything being pulled down, right? What I feel is the gravity, the normal force being pushed up on my feet or on whatever, or from your chair on your bottom that way, right? And if you're free fall, right? Are you weightless? No, you still have mg. But what's missing is the normal force if you're in free fall, right? There's no more normal force, you're in free fall, then you have no more normal force. So you feel weightless, but that's an artifact. So n is really your apparent weight, what you feel experience-wise, or psychologically speaking, right? So what you feel is really mv square v3 over r minus mg, right? So I guess it's not me, but the coaster in this case. So the m of the coaster, here you're going to plug in 10 because of the radius. You can plug in those numbers and figure out what your what a coaster's apparent, I guess, yeah, everything's a coaster at the moment. So the coaster's apparent weight. Okay. Now, let's say it went all the way through the loop, right? Also, this is assuming conservation of energy. That means no energy is lost through heat and friction, right? If there's friction, so there's no friction in this case. I'm assuming no friction. In real life, there will be friction. So what will the friction do? Friction will destroy the conservation of energy. Well, yes and no, depending on how you look at it. It does not conserve only the kinetic and potential, but actually it's conserved in the sense that if you add up all the heat that is generated through the track, the sound that is generated through this, and maybe sparks if there's light sort of emitted, this to a lesser extent, granted. But yeah, it is there, right? So now I'll leave you with 2 exercises on this. You can check with your peers on Piazza, quote this video number or example 3, and let's say you go all the way up to 25 meters again, no friction. So here you're still going to go at some speed. So let's call this 0.4. So V4 over here. Okay. So I'll put it in red. Right. So exercise part A and B. Can you find what's the speed over here? What's the maximum speed that you reach from top to bottom? And when you go through the loop, back down. Up here, V4, what is the speed at that point? Okay, and yeah, so you can also see, hopefully you'll calculate V2 and then you'll see that is smaller than this number, larger, I should say. So here, the speed would be larger and then it slows down as you go up. It speeds up again and then it slows down. And yeah, and you can also play with, if this is 30 meters, what would the speed be? Can you do that without calculation? Well, what's your intuition? If that's also 30 meters, if there's no friction, you should go all the way back up and you should be sort of just at rest, right? You can run through the math and it should be a one-line thing to immediately see that it's going to be 0. That's why I made it 25, so you actually have something to calculate. 25 meters. Right. Yeah, if you can do this, you'll sort of get a handle of energy problems, and it's pretty easy to use. And notice how friction works, right? If you actually have friction, then your total energy, where will you put the friction? So you will, at point, let's say 0.4, right? So you have K1 plus U1, and at 0.4, you have kinetic energy, potential energy at 0.4, and plus maybe heat energy at 0.4, and plus sound and whatever. Let's group all of them into sort of wasted energy. 4. Okay, so the reason you put it here, not here, is because at first you have all the total energy, and throughout the process you add these up, or you can think of it as this is the initial energy, right? If you take this, subtract these, that will equal to the sort of dissipated energy. Dissipated means sort of radiated and dispersed into out of this system, right, into the universe. So that's how you calculate how much wasted energy there is. And you see the fact that you have wasted energy by the time you reach to 0.4, so then you should add up all the heats that's generated throughout the process. You will see that the kinetic energy will be less, right? Because if you reach to given height, you cannot reach as high. That's also another reason you can think of. So in the force approach, friction is seen as it's a force that pulls you, opposes the motion, right? Opposes kinetic friction, right? It's opposes the motion. But in the energy approach, we have a different perspective of friction. Friction, yeah, we don't talk about opposing motion, right? We talk about its energy. Friction basically consumed some of its initial energy, initial potential and kinetic energy. It'll consume some of those initial energy at 0.1 and turn it into heat, sound, and whatever other things that has energy. Okay, so you get different perspectives and different things. Give that a try. And now we'll look at examples that is not kinematics, and you can still use the energy approach to do that. I think I have one more example, one or two. We'll see.